Oh, okay. Okay, so I'll try, I'm a bit sick, so I'll try to start slowly and not to be too technical, more for me than for you, but so let me start with some pictures, and then I'll switch to the Blackbird. So, so this is the way I sort of like to present in a light way this issue of green boundaries. Actually, I don't know whether you can appreciate from this picture. This is a map of Lower Manhattan of last century, and if you have been in Manhattan there is a specific metric, which is the Manhattan metric, which is the avenues and the streets. So it's a square sort of lattice in the whole of Manhattan, but in the Lower Manhattan, where Lower Manhattan shows different patches of different areas with different orientation. And this is possibly due to the fact that somehow avenues tend to align with the shore. So to create a region with a local order that are sort of coherent with the boundaries of this object. And so this is what you can recognize here. So with some red lines, I highlighted the separation between the different regions. I don't know whether you can see here, but it's really kind of clear that there are grains, okay, regions in which there is a local order, and then there are boundaries separating these regions. So this is more or less on a large scale what I will try to describe on a small scale. And the small scale, is related with a situation in which you have, again, a local order. And this is actually a simulation of sort of similar problem in which you look for the best partition of a square, best in terms of perimeter. So in terms of perimeter, the best would be hexagonal patterns, but then there is a boundary which is not completely compatible with hexagons. And so, I mean, this is simulation, so it's not a final computation, but you see that there are somehow regions in which they are hexagon oriented in a different way. Some are hexagon, some other are not. So some are sort of defects in this pattern. But again, you see something similar. So a very geometric problem, no physics in a sense, in which you observe this situation. And what I really want to describe is a situation which is more physical. So this is an image at very small scale. You see it's 2 nanometers of metal. So in fact, metals are crystals. So they are the atoms of metals are arranged on lattices, or they're structured, and in general, crystallization occurs on a local basis. So there are pieces of lattice of metals that solidified metals that appears here and there, and in principle they are not compatibly oriented, so they create regions, like you see here, regions with different orientation of this pattern, and these regions are separated by some boundaries. And here there is a picture, I mean, this is taken from the web, so there is a picture of T-shapes, I will describe this in a minute, which is somehow telling you that there is something wrong at the boundary. So this boundary has some incompatibility, some defects, as in the previous picture. So in the previous picture, the defects were polygons that were not hexagons. Here will be something else, but still, I mean, this incompatibility between the two orientations produce some mismatch. So this is somehow the picture I want to describe. And then I probably will try, if I succeed in giving the second lecture, also try to tell you something about not only a model which describes this situation of grain boundaries, so metals, polycrystals at a scale in which you see the grains and the boundaries, and somehow this case will be somehow related with a model which is a line tension model. which I will call a sharp interface model. My lectures are about variational models, so I will try to give you a number of energies that are related with this problem, right? So the first one, which is the simplest one, the more geometric one, if you want, is the line tension model. So a model in which I really only describe the boundaries between these sets. And then there will be a second approach, which is a variational model which I will call a diffuse interface model. Which in a sense contains more physics. So in a sense is able to give you a more detailed description of what happens at the boundary and why there is this sort of concentration of energy at the boundary. Why is meaningful to describe this model with a sharp interface model. So somehow the first step will be to describe a relation between these two models. So how they are related, why the diffuse interface model is a good explanation or a good derivation of this line tension model. And instead, this picture is related with another question. So it's not really describing the physics of these boundaries, but it's more find a way to identify these grain boundaries in a picture of a lattice, okay? So in this picture here that is taken from a paper by Wirth, here there is a picture of a lattice. So it's a locally periodic structure. So this is a blow-up of a region of this larger picture. And the idea is that you would like to have a way or an algorithm or a model which is able to identify the regions with different orientation, like in this segmentation over here, okay? And in general, somehow you don't really want too much physics in these models. You want a simple model to be able to describe this situation. So if I have time, I will give you some ideas of a phase field model to approximate one. So this line tension model, or at least to clean somehow this type of pictures. These are somehow well described by very classical models that I will introduce at the beginning. I mean, a bit on the lines of what Jean-François did yesterday morning. So I don't know, I didn't know what was the general level of the audience in terms of knowledge, so I prepared some introductory part. If I'm too basic, please tell me, because I saw that the level of technicalities is very different among the different lectures. So I will try to start with a simple but classical and rich model, which is a canalier model for liquid-liquid phase transition. So in that model, you find these three situations. So you find a line tension model, a diffuse interface model, a relation between the two, and the phase field model I'm talking about is what Jean-François called the Ambrosio-Tortorelli approximation yesterday. So it's a phase field model which is good in reproducing energies that are concentrated on interfaces, okay? And so with liquid-liquid phase transition, I mean, the following picture. So I'm looking for two phases, and the disclaimer is that this picture is AI generated, as you can tell. So it's two phases, and you see the separation of these two phases. So as I told you, I will give you these models for these two scalar phases, so to say. And then I will generalize, slightly generalize this to three phases. That's the reason for the AI. So three phases, so the mixture of three phases that are separated. And then I'll go back to the general case of polycrystal, this one, okay? So I think I can switch to the blackboard, apart from a last slide that I need to show, just because to make this picture is too complicated. So I will use these two blackboard for a while, and then how do I switch on the lights? Okay, let me start with a, say, baby example. As I said, the baby example is related with this liquid-liquid phase transition that was over there. And so the sharp, let's start very easy. The sharp model is an energy which I call F0 of U. U is a sort of a phase field, so it's a so-called order parameter. And this order parameter in this sharp interface model takes two values, alpha and beta, 0 and 1, where I was yesterday in the talk of Jean-François, and then the energy F0, which depends on this U, which takes value in alpha and beta, is actually measure the perimeter of the region in which, say, for instance, U is equal alpha. So this U, you want some regularity, so you take BV of your container with values in alpha and beta. So this guarantees that this set has a finite perimeter, and so your energy is the perimeter of this set times a constant. Okay? So you just measure the perimeter of this set. So you have your domain, you have a separation between these two phases, and you measure this perimeter. Okay, and in this simple situation, the diffuse interface model is somehow what is called the Canilier energy. So the Canilian energy is actually an energy which contains two features. So now the order parameter does not take values in alpha and beta, but is take values in R. Actually, maybe if you really want to give the interpretation that I'm going to say is alpha and beta, but I mean, in general, it's a real parameter. And so it's smooth. So describes somehow the concentration of the phase. And here you have two terms. One term which is given by a double well potential. So W is a double well which has zeros in alpha and beta. Then you want somehow the transition between alpha and beta being possibly smooth. So you want to go in a continuum or smooth way from alpha to beta. So you add a singular perturbation. So something that wants the phases to be as much constant as they can, but then go smoothly from one to the other. Okay? So this is what allows you to get solutions, say, for instance, with given boundary condition of this type instead of having a wild mixture of the two phases. Because if you don't have any regularity, of course, you can jump from one phase to the other without any cost. So this is telling you that going from one phase to the other costs some energy, some gradient. Okay, and then somehow you want to describe the relation that you have between these two models, so what I was calling 1 versus 2, and this is somehow done by recognizing that this energy, which I don't know, I can call the Hilliard energy of U, has a precise behavior on this type of situation. So you do these heuristics. So I'm doing this just because these are the steps, so to say, that are the main steps I will do in my model, which is much more involved. So I first clarify it in this simple situation. So the heuristics is the following. You look at a situation in which you go from the phase alpha to the phase beta, and you go in a smooth way in a region, say, of order delta. Okay, so you call U delta this test, and now you compute the energy, the Scanilian energy on U delta. So I don't make this computation because anybody who has seen this energy once have already seen this computation, but turns out that the best way you can optimize the energy with this type of configuration is to choose the transition of order epsilon, and then you compute the energy with this choice of delta, and you get that both terms contribute with epsilon, so that the energy of this configuration with delta order epsilon goes as epsilon. So the idea is then the one that is the origin of, I mean, is the basic starting point for the asymptotic analysis of this energy. So the idea is there by Modica and Mortola. I start from this energy and rescale it and produce this energy that also Jean-François was calling Modica-Mortola energy. So the Modica-Mortola energy is 1 over epsilon, the Canelian energy. So it's 1 over epsilon okay, and now once you have this, you can show that that this converges, so gamma converges with respect to the L1 norm. So this is an energy which is, so for instance, well defined in U, if you have U in H1 of omega. At this level, omega is an open set of RD. And it converges with respect to the L1 topology to this F0, so to some constant which depends on the potential times the perimeter of the set where U is equal alpha. So I'm not sure, but I believe that I shouldn't say anything about gamma convergence. Everybody knows what gamma convergence is? Yes, maybe. So the only observation that I want to make is that, as you know, gamma convergence is related, so it somehow is related with the variational analysis in the sense that if you have gamma convergence of an energy to another energy and you have a compactness statement, you also have convergence of minimizers and minimum problems. So in this sense, it's a good variational approximation. And so a key step is what we call the compactness. So compactness in gamma convergence somehow is the property that guarantees the convergence of minimizers. So somehow tells you that this approximation is robust, so it's really related with the minimization. And also is the first property that tells you something about, say, the domain of the gamma limit. So it tells you which are which is the characteristic behavior of sequences with equibounded energy. So in general, if I have gamma convergence of a sequence of functional to another with respect to a given topology, this compactness statement is the one in which you prove that if you have, say, equibounded energy, then up to a subsequence, you have a convergence of u to some given function, like limiting function u0, and say the space in which this u0 belong tells you which is the space in which the gamma limit is finite. So somehow which are the configuration that you are going to detect with the limiting of equibounded sequences. So this is really the starting point. And then I had this picture with the multiphase. So let me tell you how do you generalize this. So there has been the literature in the context of this liquid-liquid phase transitions is huge. There are many level of generalization, anisotropic, and multiphases, and so on. So I really want to combine all these features and tell you something about what I should have as a multiphase sharp interface model. So in principle, a multiphase sharp interface model is related with the situation in which you have your container, as in my picture, and you have boundaries of different domains. In each domain you have a different label, which may be a scalar of the parameters or a vector value of the parameters, depending on the problem that you want to describe. So in principle, already an energy of the form of modica mortola with W, which has zeros in these points, is able to produce an energy which is a sharp interface model for this type of situation. So the general one that I want to describe is an energy, which now will be defined on functions. Yes. So I'll take zeta, which is the set of admissible phases. So this will be defined on functions BV with values in zeta. And so will be an energy which is defined on the jump of this function, as in this picture, J of u, and in principle may depend on the values of the phase on the two sides of the boundary and on the orientation of this boundary. So at this level I'm in RD. Okay? Actually, this is a good description of what I want to describe in a more complex situation. A good example of what I want to describe in a more complex situation. And let me tell you what are the key ingredients in order to make this problem well defined. As you all know, as I said, in principle, you can approximate energy of this type with diffuse interface models. And as you all know, if an energy is a gamma limit, it must be lower semi-continuous with respect to the topology that gives you this gamma limit. So the basic property that makes these sharp interface models lower semi-continuous are actually quite, implicit. So the property that is needed for this energy density in order to make this problem lower semi-continuous is the so-called BV ellipticity. So phi should be BV elliptic. And this was introduced by Ambrosio and Brides in the 90s. Specifically in the case in which Z is a discrete set. So really what I was describing here, a finite number of faces well separated. Okay, and this BV ellipticity is somehow similar to, so I'm not going to really give you the precise definition, even though in principle it's not that complex, but it's really similar to what you find in nonlinear elasticity when you see the properties of energy density depending on the gradient in order to have lower semi-continuity in sublet spaces. So the quasi-convexity. So it's a problem that tells you that if you minimize this, essentially that tells you that if you minimize this energy on a box in a given orientation with two given faces at the boundary, the sharp interfaces or the straight sharp interfaces are the only minimizers. So in particular, this BV ellipticity implies two main properties. One is the subadditivity, which essentially rules out the following situation. So if you want to approximate this configuration with alpha and beta, you want to somehow avoid that it is more convenient to introduce an intermediate phase gamma and shrink it in order to have a better energy. So an energy of a sequence like that should not be slower than this energy, okay? So you don't want that, say, F0 of this is greater than the limit of F0 of that, okay? So, and this means that you don't want that alpha, so you somehow want, the subadditivity is telling you that phi of alpha, beta, ni is always less or equal than phi of alpha, gamma, ni plus phi of gamma, beta, ni. Okay? So this inequality guarantees that this is never possible. It's never possible to construct a sequence in which you approximate the sharp alpha-beta configuration with something which has a different structure, macroscopic structure. So this is the first property you always have. And then you have some sort of compactness. Sorry, not compactness, some sort of convexity in the orientation of the boundary. So this will be null, right? And this is something, this convexity, I'm not really going to write it, but so the convexity is telling you that if you want to approximate this configuration, this should not be convenient, okay? So it's not convenient, so Jean-François was calling it oscillation at small scales. Now you want to avoid that oscillation at small scales produce an energy which is smaller than that. So you don't want that F0 of this is greater than F0, so that the limit of f0 of that. Okay? And so this is this requires some convexity property on this nu. Okay, and this is the case in which you have so how does it work here? Okay, this is the case in which you have a discrete finite number of phases, and but this is not the case I want to treat, because actually my picture at the beginning was made of domains, in which the label of each domain was a sort of rotation of a given structure. So what I really want to treat is a case in which Z, and this will be done soon, but Z is actually a set of rotations in S2, for instance. So from now on, just to make this, so my models are all in dimension 2. Let's do it in general for the moment. So a set of rotation in dimension D. So think about D equal 2 or 3, just to have a clear interpretation. So now what I really want is that my energy, F0, which, so from now on the order parameter would be capital A, okay? So capital A is the phase that tells me which matrix I'm taking in each region. Should be, as before, the integral on a jump of A intersection with omega times some function that again depends. So it's a similar structure. And here my function should belong. So I mean, the picture I was describing before was always a domain with a partition, right? And the partition, each set of the partition was labeled by one possible phase. And I didn't have to specify anything else, because this is what the structure guarantees. So if you are BV and you take discrete values, the only possibility is to be a partition, discrete and finite number of values is to be a partition. But this is not the case when you have values in a continuum set, so to say. So here I want to add some structure. So I want to say that my set of parameters belong to, my order parameters belong to SBV that I will call 0 of omega with value in Z or SOD. And with this, I mean the function which are SBV with value in SOD and 0 absolutely continuous part of the gradient. So no gradient, no diffuse part. And I don't need to say what SBV is, right? Or do I need it? So actually this is, I don't want to be too technical, but you know what BV is, right? Okay, and you also know that there is a structure theorem that tells you that functions that are in BV, so functions that are in BV means that gradients are in the sense of distribution, are measure of bounded variation. And these are not all possible type of measures. Actually, if you compute this measure, there is a precise decomposition of this measure. This is the structure theorem of De Giorgi that tells you that the gradient of this function has three parts. One is a diffuse part, so the one that we call nabla A, which is a measure which is absolutely continuous with respect to the Lebesgue measure. Then there is a jump part, okay, So A plus minus A minus, something like that. And this is concentrated on a d minus 1 dimensional set, which is what I call the jump. And then there is a third part. So the last part is an intermediate, in terms of dimension, part, which we call Cantor part of A, which is a measure which has a support, which has a dimension between d and d minus 1. So the Cantor Vitali function is the typical example of a function which is BV and has only Cantor part. So SBV means that this part doesn't exist. So this is SBV. So only jump and diffuse part. So essentially, my SBV0 is not even this. It's only jumps. Okay? So more or less something like that, which is not true. It's more or less because having only jump does not guarantee that you really have a partition. So the idea is that I want something like that with different orientation. This is the typical situation I have in mind. Then, in fact, there are sort of crazy examples in which you may have a function that belong to this set, but for which the region in which you are sort of constant do not have finite perimeter, so that they may have many pieces. Okay, because actually what prevents to have many pieces in this case is that the jumps the jumps between two faces are always they have a minimum of height that can have, because you have a finite number of jumps, right? So every time you compute the gradient over here, you say that the gradient is a finite measure. The gradient measure the difference between two faces and the length. So this guarantees that the length of these interfaces is finite, so to say. But then if you can make small jumps, so if you can go from one face to the other moving very little, you can make many long jumps without pain in the total gradient. And this is exactly the point in which we need an extra property for this energy to be well defined. And this extra properties requires somehow to say something about the behavior of this energy density at zero. So you don't want that when you make that you can make very small jumps producing a diffuse gradient without paying too much energy. Okay? And so the example, so let me give you the example in 1D. So the example in 1D would be that, and let me make the example in 1D and with z equal r. So I mean, forget about the rotation. So it's really an issue on having. So I'm talking about SBV0 with values in r. So it's an issue of having a continuum possibility for the faces. So here my function would be the sum over the point in the jump set of u of psi of, say, make it u plus minus u minus. The simplest you want to imagine. And so now suppose that you have you can approximate say in 0, 1. So now you can approximate the function L times x with n small jumps. Okay, so you take n jumps at distance 1 over n. So this means that the jumps, the length of the height of the jumps is L over n. Okay, So now you compute the energy of this sequence. And the energy of this sequence is n times, so it's n times psi L over n, which is the height of the jump, right? And so you see immediately that this is psi L over n times L over n times L, okay? And this, if n tends to infinity, in principle, converts to phi prime of 0 times L, okay? So if you have that the derivative of psi at 0 is finite, this sequence will have equibounded energy because it converges. And in fact, what is true is that this energy is not well defined in this set because it relaxes. It relaxes means that if you look at all, so if you take the gamma limit of the constant sequence, you get the relaxation. So the lower semi-continuous envelope of this thing in BV, and it relaxes in BV. Essentially with this sum over the jumps at which you have to sum psi prime of 0 of the rest of the derivative, okay? So u prime plus, so this will be u, if you want, the integral over 0, 1 of u prime of x plus a prime of the, say, Cantor part, how do you call it? Cantor part of 0, 1. Okay, so you take the measure diffused and the measure corresponding to the Cantor part linear with this coefficient. Okay, so this is the relaxation. So essentially, if you want to rule out this situation, you have to require that this energy density does not allow this situation. So and the right property is exactly this behavior at 0. So you want this behavior at 0. You want the infinite slope at 0. So in general, you want that, so in this specific one, the example, you want that this slope is plus infinity. And this is the same property that you want for this energy. So this energy should be BV elliptic in order to be low semi-continuous. And if you want this energy to stay in this domain, so to give finite energy only to configurations which are sort of partition, you want that small jumps are never convenient, so that the slope at 0 of this energy density is plus infinity. Okay? I'm going too slow. Okay, so this is the model I want to consider for polycrystals. And so let me go to the derivation. Can I show a couple of pictures before? No, in fact, I need to also okay, I'll show the picture and then I'll give you. How do I erase the blackboard with this one? Or okay. Okay, so now I'm back to this polycrystal structure. Okay, so let me. Let me set the main the main features. Sorry, it was just the light. Which one is the light? Okay, yeah. So actually, the main feature are the following. So the key point, the key starting point. As I said at the beginning, metals are crystals. And actually, as I said, there is a reason why they are crystals, and the reason is that the atoms are, so to say, happy if they see around them a periodic environment given by a precise structure that depends on the atom you are considering, the type of metals that you are considering. So in general, they are polycrystals, in the sense that they have local ordered orientation, structure. And then, due to this crystalline structure, we really have, so this crystalline structure, so to say, is the paradigm of continuum mechanics. So the idea is that you define what elasticity or plasticity is in continuum mechanics based on the assumption, on the knowledge that at the microscopic level your material is ordered. Okay? And so in this way you can identify elasticity versus what we call plasticity. And elasticity is simply based on this schematic, very simple idea. You have an ordered structure, you distort this ordered structure. So you slightly move the atoms from the, so the crosses are the atoms, from the equilibrium configuration, the zero energy configuration, and this configuration is completely reversible. So you go back and forth. So if you release the stress, so the forces, this goes to the original configuration. So this means elasticity. So this means that when you are in this configuration, you have some sort of energy which is stored, which we call elastic energy, which somehow gives to the atoms the forces that are able to rearrange in the original configuration. Okay? And plasticity instead is related with a similar configuration in which you sort of increase the stress, so you give enough deformation in order to produce the following situation. So maybe I should have also put a picture of this, but I didn't. Okay, so imagine that this is the situation you produce. Okay, so exactly the same counting of atoms, you apply a force, and not only you distort, but you also slide on some specific, in some specific direction. So you go in this direction, so you apply a force, and then here you still, I mean, locally you have an elastic distortion. So locally you still have some stored elastic energy that somehow bring the atom to sort of a local minimum. But then when you release, you don't go back to the original configuration, but you go to this staircase configuration. Okay? So this is what you call a plastic deformation, which is irreversible, because there's no stored elastic energy over here. Each atom sees, so to say, around it a local order, so it's happy and no elastic energy. Okay. Okay. So this mechanism is important because it's really somehow at the main mechanism for plasticity and elasticity. And another thing that is important to know is that in this situation there are defects. And in particular, there are defects both when you do this kind of deformation, so it's never really true that, I mean, here there are 3 atoms, but then you imagine that you have, a billion of atoms that you have to slide on one given direction. You don't do that all at once. So this is really local effect, and so you create defects. So, and these defects are actually also related with this situation over here. So you have order structure, and then this T-shapes is a line of defects, and that's the reason why here I need a slide, because I tried to make this picture my own at the blackboard, but I don't succeed. So, so yes, which one is this? Okay. Okay. So, so this is taken from the original paper of Reed and Shockley in the 50s. So in the 50s, there are a number of interesting papers. Actually, surprisingly, this idea that metals are crystals and the idea that defects are a key ingredient in the description of the crystals is relatively recent. And in the 50s, really, people are starting to say these atoms, these structures at the microscope, so they really had the evidence that these metals are crystals, and so there is a number of interesting models coming from mechanics which describe, for instance, the interface between incoherent materials. So, for instance, at the grain boundaries. Okay, so this picture is a way of explaining why, in an interface, especially with a small angle, which is the case we are interested in, small angle grain boundaries, there are defects, and why they play a role. Okay, so suppose you have your cartoon crystal as here. Now you cut a line, which will be your interface, and you rotate these 2 pieces by a small angle, okay? Like here, this theta over half. Can you see that? Okay. Now, actually, if I really do that rigidly, so if I cut and I rotate, I open a sector, right? And instead, in this picture, there's no sector, okay? This field of atoms. And how do I fill it of atoms? I have to introduce extra atoms. And the idea behind this model of Reed and Shockley is that the most convenient way of filling this gap is to do it in a sort of periodic arrangement in which, okay, this pointer is not always, okay, in which from time to time you add an extra line of atoms. So you see, this T-shape is the beginning of an extra line that does not continue over there, okay? And again here, there is an extra line of atoms. So there is an extra line, there is an extra line, there is an extra line, there is an extra line. This periodic insertion of an extra line of atoms gives you enough atoms to arrange locally in a sort of distorted perfect lattice, okay, and fill the gap. So these are the objects that are relevant for this description. These defects are called dislocations. And are exactly the defects, I am almost finished, I think, with this, are exactly the defects that I was mentioning here. So when you do this, when you slide many atoms, sometimes you accumulate an extra line of atoms because you don't really slide by the whole line. And so actually materials are full of these defects. And in particular, the idea is that when you are at the boundary of a grain boundary with small angle, there are many of these defects that are somehow due to the fact that you want to fill the gap, but still locally be as close as possible to a perfect lattice, up to some particular region. And so the computation I want to make today is about this derivation. So it's trying to give you a model, which will be a diffuse interface model, which will possibly contain some physics that explain why, if you see the grain boundaries in this way, you will obtain, this is a shape which is, here you cannot say, but is sort of the energy per unit length, something like that. So this is the shape of the possible energy depending on the angle at which you tilt the two interfaces. And you see, I mean, in this picture there is a sort of infinite slope at 0. And actually this infinite slope has a specific structure. I didn't write it here, but is, say, theta log theta. Okay? So I want to give you a model which has some physics to explain why at this small angle grain boundary you have this theta log theta. I think we can forget about the screen. I mean, you can imagine that it was not easy to do this picture at the Blackboard. Sorry. Okay. Okay, so I think I need to start with a bit of the ingredient of this physical model. Or maybe I can... Wow. Okay. So, okay, let me start with some elasticity. Okay, so actually, elasticity versus material defects, if you want. So what are the basic model? So as I said, elasticity means that if I have my distorted domain, I assume, so the basic idea behind the continuum mechanics description of elasticity is that a material, which is, so this is a macroscopic body, so in principle it's a continuum, no? It's continuum mechanics, so it's a continuum body, but you believe that this distorted body has a lattice, which is distorted, so you map it on the reference configuration, and somehow you describe how distorted this domain, somehow measuring the distance between the distorted lattice with the reference configuration. So actually in continuum mechanics what you do is the opposite. You take your reference configuration, you map it in your deformed configuration, and what you call either you consider linear or nonlinear displacement or deformation, the map U is the map from the reference configuration to the deformed configuration. Actually, the map I'm talking about is the inverse. So you have a distorted material and you go to the zero energy configuration, and the energy I mean, this is an assumption on the material, hyperelasticity. The energy is measured in terms of the reference configuration. So it's an integral over the reference configuration of some energy density of the gradient of U. Okay? And this energy density has some basic properties. For instance, if you compute on a given matrix F your energy, and you rotate by by a rotation, you shouldn't change the energy. And this is the framing difference statement. For instance, a good candidate that we will use is distance squared from the rotation. Okay. Okay. So maybe from now on I will be in dimension 2, even though if this elasticity part is general, but let me stay in dimension 2. Okay, so what are in dimension 2 these defects instead? So let me describe the defects a bit more in detail. So the T shape that we have seen in this picture was the following. So you had an extra line, and then something like that, right? Okay, so the extra line of atoms, which might be responsible, might be the result of a non-uniform slip, for instance, is this one, okay? And then here you see that if you look at, for instance, this cell or this triangle, this cell can be mapped on a square lattice. I mean, I'm talking about a square lattice, not, I mean, in general, they are not squares, but from the mathematical point of view, square lattice is more than good. So you can map in an affine way this cell to that. Okay, so somehow this is elastic, if you want. So you can find, and that's the reason why, in general, elasticity is represented by a gradient. The idea behind elasticity is that you don't change the structure of the lattice, you just distort it. So you triangularize if you want your ideal lattice that you have behind. This is a continuum model, so there are no lattices. But if you have it, at a small scale, you make a triangularization, and each triangle goes affinely on another triangle. And this affine map is so the local gradient of a piecewise affine map that moves this energy to this configuration to that configuration. So now you make it continuum, this piecewise affine becomes a continuum function with a gradient. Okay. So here you measure the energy of this quantity with this affine map, and you can do it everywhere. So everywhere, in principle, you can construct this piecewise affine map. Okay, but here you cannot. Okay, so this cell, for instance, has these 5 atoms, which are not, you cannot really map on a square or in an affine way. Okay, so you don't do it. You simply give up on doing that. So you remove the regions in which you cannot do that. Okay, but you want to say something about this region, and now instead of comparing this region with an affine deformation, now you do the following. You keep your reference configuration, and you start moving around this defect, like that, and you repeat the same path in the reference configuration, because locally they are close to, so this is close to a square, so you start here. Then this is close to another square, you go here, then you go there, and then you repeat the same path. And now I have to add an extra line. Now you repeat the same path over here, right? And then I go here, and then you see that there is a gap. Okay? So I don't close the path. So if I go around a defect here and I do the same thing in the reference configuration, I don't close the path. So this is simply telling you that this piecewise affine map that you create over here, or if you want this piecewise constant map with values in matrices, which you create here, is not a gradient. So if you do the circulation of this map around this defect, you don't have zero co-circulation. Okay? So in this sense, this is telling you that these defects are topological defects. And so which are the ingredients, the main ingredients of my, I didn't use this blackbird in a very efficient way, but so what should I say, relevant variable, if you want, main variables, relevant. So there is one variable, which is the one I was trying to describe, which is a map, which goes from omega, which is my domain. Actually, so let me call omega tilde here and this omega. Okay, there is a bit of confusion because in general, so the typical behavior, the typical energy that you consider is is on the reference configuration. Okay, but if you really look at books in continuum mechanics, they start with an energy in the deformed configuration. So the right thing to do is to look at the deformed configuration because the energy is in the deformed configuration. Okay, then somehow assuming, so to say, that this map over here is invertible, you can translate everything in the reference configuration, which has the advantage that does not change if you change the loads and so on. The reference configuration is given. Okay, but from now on, let me consider this as my starting point. So I will work on the deformed configuration because my domain is the polycrystal, if you want. So I don't. Not the reference is just a local way of measuring things. Okay, so I have my domain omega, which is my possibly defected domain, and I have a map which goes from omega to 2 by 2 matrices, which ideally represents, so it's a continuum variable, but ideally represents this matrix that you need at the local level to deform a given triangle of the lattice to a reference triangle. Okay, so for the moment we simply assume that this is an L1 function, and so this is the local distortion, and then there is a set that I call S, which is the set of incompatibilities, which, if you want, in this picture would be a neighborhood of this point. So in a continuum model, you should imagine that you have your domain, and then there is a point in which there is a problem. So outside this point, outside this point, you have a perfect map, an affine map, or a continuum map, and inside this point there is this set, which is a closed set. So the incompatibilities defects, which in this picture somehow is a neighborhood of this T shape. So let me convince you about this say picture with this formula, with an example which is an explicit formula. Okay. So maybe this is too basic, but I don't know. I don't want to lose everybody. So let me do it. Just to show you what type of example of defect you may have. Suppose that the point I take a point x0, which is 0, and then I take a field beta, which is 1 over 2 pi. E1 tensor product x orthogonal over x squared. Okay, so this is nothing else than the following matrix. Okay, so it's a matrix squared whose first row is the typical example of a field which is rotational but not conservative. So the component of a form which is close but not exact, right? And the second one is 0. And so now, and then I take A, which is identity plus beta. Okay. Okay. So what is so this field is well defined up to 0. And now if I take the circulation of this field on a ball centered, on a circle centered at 0, A, so it's the line integral on this boundary. So this is E1, okay? Because the circulation of this is the typical the typical example in which the circulation is 2 pi, okay? And this one is 0, so it's E1. So it's exactly like here. If I do the circulation, I have a vector, okay? And this vector in this case is minus E1 in my picture, but that's why. In general, this vector is the so-called Burgers vector. It always belongs to the lattice, so to the lattice structure, and this is a sort of multiplicity of this defect. Okay, so depending on whether, for instance, you insert an horizontal or vertical lines, you get E1 or E2, or you can get multiples of this. For instance, if you do the circulation around 2 of these defects or 3. Okay, and so this is telling you that if you take the curl row by row of this field A, you essentially have E1, which in this case is the Burgers vector of this defect, delta at 0. Okay, so in general, fields with this type of defects are fields which curl is a measure that might be concentrated. Okay, so and this is the condition for being S a set of incompatibilities. S, say if you want, curl of A is a measure, in D prime is a measure, and the set S contains the support of curl of A. Okay? So in this specific example, this would be A, and S will contain 0. That would be a neighborhood of 0. So this means that outside S, this is a local gradient. Okay? So this means that if I want to assign an energy to this configuration, no. They are one, never together. Okay. So if I want to assign an energy to this configuration, I can assign the following energy. The integral over omega of the distance squared of A. So this will be my energy A to the pair, associated to the pair A and S. So it's the integral over omega minus a neighborhood of S of the distance square of A from SO2. This is the elastic energy. Okay, so this is really what I was doing before. Locally, the elastic energy is an energy density that depends on a gradient, and in fact, outside SA is a gradient. I put a neighborhood for a reason that I will show you soon, because this epsilon neighborhood is reminiscent of the fact that somehow behind this there is a structure with a scale epsilon, which is the lattice scaling. Okay? So this epsilon is reminiscent of the fact that the scale of the problem is epsilon. And then, actually, if I believe that this energy should really count all the interaction between all the atoms, okay, the interaction between atoms which are close to a reference, which are an elastic distortion of a reference configuration, is measured with this integral. What is left is the interaction of the atoms which are inside this neighborhood, and these are brutally measured with the measure of this neighborhood. Okay, so this is what we call the core energy. So it's the energy corresponding to the regions in which you have these defects, which might be smaller, I don't know, but at least is a constant times the number of atoms, if you want. It's proportional to the number of atoms which are in this region. Okay, so this model complemented with a condition which somehow tells you that the circulation cannot be whatever you want, but should be always related with the fact that you have an underlying lattice. So there is an extra constraint which tells you that if you do the circulation, so if you have your set S of incompatibilities and you do the circulation around this set of A, then this should belong to a lattice vector where epsilon is the length of the lattice. Okay? Okay, this model was introduced by Lauteri and Lucaus in an unpublished paper which is on archive in 2017. Actually, they have a more general condition over here, so a less structured condition, which is actually the Lauteri-Lucaus constraint is simpler than that. It's just that the circulation should be so either strictly greater than epsilon in modulus or 0. Okay? So either you don't have incompatibilities or you have at least a quantum of epsilon. But if you make it more precise, somehow you describe very well the situation by assuming that the circulation should be a Burgers vector, so in the lattice, and the energy is made by these two quantities. And they introduced that just really in order to study small angle grain boundaries. I'm very late, I'm sorry. So I will make 2 lectures of what I was supposed to do in one. So small angle grain boundaries means that they take their energy and they take the infimum of their energy with the condition that, well, I mean, let me explicitly write the domain. So here, this is depending on the domain omega. Okay, so they take their energy on a box of length L. Okay, and on this box they assume some boundary condition. Okay, so they assume that on this box of length L the field should be a rotation by a given alpha on a side and a given minus alpha on the other side. So the idea is that they want to have a rotation by alpha here, a rotation by minus alpha here. So they want somehow the lattice align here, the lattice align there, and they want to see if the minimum somehow shows an energy which would be an interface, and they want to compute the energy of this interface. So the idea behind the result is that this energy should be able, once you minimize with this boundary condition, so assuming that on the sides of this domain you have two given orientation which differ from an angle alpha, and this alpha is small, okay? They want to see what is the behavior of this energy. So this in principle should give you the energy density of a small angle grain boundaries with small with alpha 0, which they hope is the alpha log alpha behavior, which is the Reed-Shockley law. Okay? Okay. So I was supposed to do some heuristics with this model, but I don't have time to do the heuristics on this model. I just give you the less aspiring one, so to say. So the idea was to give you the same heuristic that one should make for modica mortula. So try to understand what should be the right configuration, the minimal configuration, and so see which is the right scaling for the energy. And so I give you just 2 steps, and then the other 2 will be done tomorrow. So the first one, let me try to produce a number of competitors, if you want, for this problem. So the idea is that this minimization will be able to reproduce an energy density. So this will be so the result, if you want, will be that this energy should give you an energy density that in alpha depends on alpha log alpha. But let me go slowly. So competitors. So I'll give you the 2 wrong one. So the first one is the elastic. So in principle, you can produce this rotation at the boundary by just distorting everything, right? And so this is, so essentially the idea is that you are connecting a rotation by alpha with a rotation of minus alpha with something which is a gradient, okay? And since it's a gradient, and this will be done a bit more in detail tomorrow, since this set is rigid with respect to gradients. So if you want to connect 2 rotation with gradients, you are always outside the rotation, okay? So this means that the energy of a field A, which is always a gradient, and at the boundary is 2 different rotations, is always at the given distance, is always outside the rotation, the set of rotations. So this means that in the whole box, this thing will be bounded from below. At least, half of the box with this thing will be bounded from below. And so this means that the energy of A, S, so S will be, so this will be gradient of U, empty set QL, essentially will be a constant times L square. Okay, because essentially in the whole square or half of the square, you have this is bounded from below, this is 0, okay? This is bounded from below, so the energy is the area of the box, which is bad because it doesn't scale like the length, because you want an interface, so you want this energy scaling like a length, which is the length of the interface. Okay, so let's try another naive, and then I close. Sharp. So in principle, this allows you to do also the following thing. I cut region and I rigidly rotate here and there. So essentially, I take a box in which A is a given rotation by alpha here, a given rotation by minus alpha there, and this is the set S. Because, there's no constraint on S to be really a dislocation, or it's a set of outside which you don't have elasticity. So S is this length, and here this energy is 0, because it's a rigid rotation. So A on alpha is a given rotation, and the other alpha is the given rotation, so the other given rotation, so the elastic energy is 0 because it's completely rigid. The only term that survives in this energy is the area of this this neighborhood of S, which is the length, which is essentially a neighborhood of this set over here. So the energy, the total energy of my A with this S in QL is now L, which is this length, times epsilon, or 2 epsilon, whatever, 2 epsilon. Okay? So, and this I conclude. This somehow tells you that this model is able to reproduce a line energy. So this is for L large, of course, this is better than that. So this competitor, even though it's a bit rough, is a line tension, so it's more convenient than elasticity. And so this tells you that this in principle able to reproduce a line tension, and that the right scale in order to obtain something from this energy is 1 over epsilon. So the idea is that, and then I'll conclude, Lauterio and Lucaus show that if you rescale by 1 over epsilon, this behave like a constant that depends on alpha, which will be my psi of alpha times L. Okay? I think I concluded. Sorry for being late.